Okay? But if you have sine squared x plus cosine squared x equals 1, that means sine squared x is 1 minus cosine squared, and cosine squared x is 1 minus sine squared. You can manipulate that and get, I guess we'll do it this way. Tan squared x, secant squared x minus 1, and cotangent squared x, I'll move out of the way in a second, is cosecant squared x minus 1. Sometimes you'll be substituting for secant squared, that's 1 plus tangent squared. And sometimes you'll be substituting for cosecant squared, that's 1 plus cotangent squared. You should be able to move the 1 back and forth. I'm not going to do it for you. Sometimes you will, instead of using sine squared equals this, cosine squared equals this, you'll use a different substitution. It's the double angle formula substitution, where cosine squared x is 1/2 1 plus cosine 2x, and sine squared x is 1/2 1 minus cosine 2x. How do we know which one to use? We're going to go through that in a minute. Okay? Those are the 6 main trig substitution-y thingies you're going to want to be able to do. Now, how do we know which ones? You basically have sort of 3 categories of trig. You're going to have sine mx, cosine nx, where both are even, both are odd, and guess what the third one is going to be? One of each. Okay? When both are even, you're going to use these. And when I say both, by the way, if you only have a sine power or a cosine power, it's going to be the same kind of rules. If it's sine to an even power or cosine to an even power, or both of these are even, you're going to use this substitution. So these are the even ones, and these are the odd ones. And remember, sine squared is just 1 minus cosine squared, and cosine squared is just 1 minus sine squared. So when you have one in the integral, you can always turn it into the other one. Okay? It's just a little flipping around. I'm going to put these lights on. Maybe it'll be, I don't know if that's better or worse for the camera. Shannon, does that come out better?
Yeah.
It does, okay. So let's do some of each flavor. So let's say I have sine to the 5th x cosine cubed x dx. So notice they're both odd, okay? So when they're both powers are odd, you're going to end up using one of these trig substitutions. Now the truth is you could substitute for either one, but since cosine cubed is a lower power than sine to the 5th, let's rewrite the integral and work on cosine cubed. So so we leave the sine to the 5th the same. And cosine cubed, now we're going to want to use our cosine squared substitution. So let's make it cosine squared x cosine x. Why do we want to do this? We want to do this because what we've done now is we've got a cosine by itself. The derivative of sine is cosine. The derivative of cosine is negative sine. Okay? So if everything else is sine, then we can just do u substitution, because these are all going to be sines, and that'll be our du. So rewrite that cosine squared, 1 minus sine squared x, cosine x dx. Okay? So again, how do I know to do this one? Because I see the odd powers. And by the way, it wouldn't matter, by the way, if sine was even, that still would be fine. Okay? Because I'm going to be rewriting this one. That's where the odd power is going to help out. All right, let's do a u substitution. I'll wait till everybody's caught up. Let u equal sine x, and du equals cosine x. How do I know to let u be sine? Because these will all be u's, and that will be du. Okay, I don't want to have du to a power. That wouldn't make any sense. Yes? The general rule is a higher power is equal to u. You certainly could have done it the other way. It's just messier. Because remember, in the end, sine and cosine are really the same thing. You remember the sine curve, right? Sine curve does this. Cosine curve does that. It's just shifted. So they're really kind of the same function. I mean, they're not. They kind of are. So inside the integrand, it doesn't really matter. So it's just easier if you pick the lower power. Yes? Say it again? This one? That should be correct. It's 1/2 1 plus cosine 2x. 1/2 1 minus cosine 2x. I hope it's right. Okay? All right, so let's substitute in. So sine to the fifth is u to the fifth. 1 minus sine squared is 1 minus u squared. And cosine x dx is du. Don't forget the dx thing, okay? Because sometimes you're going to be substituting for dx, like an integration by parts. So everything has to get substituted. This is a simple integral. It's simple for me, but it should generally be simple for you. Distribute that u to the fifth. And we can integrate that. We can always do powers, right? Any polynomial. That's u to the sixth over 6 minus u to the 8 over 8 plus a constant, and then substitute back. So that's sine to the 6th x over 6 minus sine to the 8th x over 8 plus a constant. Shannon, are we zoomed in enough? Mm-hmm. Can you see that? Okay. So apparently the last video was just back a little too far. It's trouble seeing it. Ethan?
Yeah, so you substituted cos for sine the other way around.
Yeah, if I wanted to do it, look, here, I don't want to mess with your heads, but I could have made this sine to the fourth times sine times cosine cubed. Then I'd have sine squared and sine squared. So what happened is I would end up with a 1 minus u squared times another 1 minus u squared, which is messier. So that's why you want u to be the higher power and du to be the lower power. Okay? Just as they told you in church, always go with the higher power. That was pretty bad. All right. So far, so good? Some of you may feel you need that higher power after this course is over. All right, so we did an even-odd one. Now, what about odd-odd? Well, this was odd-odd, sorry. If this was sine to the sixth, that wouldn't have made any difference, would it? Because you would just have a u to the sixth here. So it doesn't really matter if you have even odd or both odd. The key is whether one of them is odd. Okay? So I'm going to have you practice one, and then we're going to do an even-even. Let's do cosine to the 7th x sine cubed x dx. So everybody practice for a couple minutes. Make sure you've got this down. And I'm going to leave the rest here in case you need to have a reference. We ready? So this is just like the last one. All you have to do is rewrite this. Okay? So if you see the sine cubed, this is now going to be sine squared in sine. And again, I could have changed the cosine to the 7th, but that's much more work. And now I'm going to do almost the same substitution, except it's going to be the other way. So u is cosine x, du is negative sine x. The negative isn't really that big a deal, but got to get it right. So we now have cosine to the 7th x is going to be u to the 7th. Oh, I didn't make the switch yet, sorry. I left out a step. Cosine to the 7th x. Sine squared will be 1 minus cosine squared. Sine x dx. Now we can substitute everything. So So the cosine, 1 minus cosine squared is 1 minus u squared, and sine x becomes minus du. Okay? Did you forget the minus signs? Yeah, you hate that. So this is negative u to the 7th plus u to the 9th du. That's negative u to the 8th over 8 plus u to the 10 over 10 plus a constant, and then put the cosine back for u. So you should be feeling better about these now. Okay, we like these now? Yeah, it's okay. It's not great. How are we doing so far? You know what's coming next? Evens. Evens are a lot less fun. And I said the even rule applies to whether you have just a cosine or a sine, or you have both cosine and sine. And these are messier, so we generally we can't give you a very high power. It's too much work. But we could give you something like sine to the 4th x dx. See, now here's the thing. Suppose you took out a sine x, like we did on the last one. You'd be left with a sine cubed. And you don't have a substitution for sine cubed. You could have a sine squared, but you'd be left with a sine somewhere in there. So you can't use this substitution. So you have to use this substitution, which is a lot less fun. So this is sine squared x squared. And that's going to, now we're going to take sine squared and we're going to replace it with 1/2 1 minus cosine 2x dx. So we can get 1/2 1 minus cosine 2x squared dx. Who's calling me? Huh. Don't call me. All right. You all see that? You don't need the square brackets, but they're fancy. I'm sorry? Question? No question? Okay. People just sort of yell things out. Or maybe I'm losing my mind. So 1/2 squared is 1/4. Now, you have to FOIL that out. That's 1 minus 2 cosine 2x plus cosine squared 2x dx. So remember what I tell you about constants. The quarter isn't important. It's just quarter times the whole thing. So you could put the quarter outside of the integral. And we look at this integral and we say, well, integral of 1 is easy. That's just x. The integral of cosine 2x is easy. That's just going to be sine 2x over 2. So this is the messy one, because it's cosine squared 2x. So let's break this into 3 integrals. Let's do 1/4 the integral of 1 dx minus 1/4 times 2 minus 1/2 the integral of cosine 2x dx plus 1/4 the integral of cosine squared 2x dx. Now there's always somebody who's a little behind and had their head down. So the 1/2 is because it's 1/4 times 2. Okay? And we got that. So I distributed the quarter and I broke this into 3 integrals. I did 1/4 times 1, 1/4 times 2, and 1/4 times 1. And I have the 1, the 2 cosine 2x, and the cosine squared 2x. Are you with me so far?
No.
So this integral is just 1/4 x. And this integral is 1/2 sine 2x over 2. So that's going to end up becoming sine 2x over 4. And now what do we do with this last integral? Well, you go back and you look at the double angle formula here. this is x, this is 2x. Remember, x is just a whatever, okay? So if this is 2x, this is 2 times 2x, or 4x. If this is 10x, this would be 20x. So however many x's you got here, it's just double here, because this comes from the double angle formula, okay? So it doesn't really matter, because a lot of people get lost on this. That's x, that's 2x, okay? So since here I have 2x, I'm going to have 1/2 1 plus cosine 4x dx, okay? Because this angle is always double whatever that angle was. So whatever the angle is when you're doing the cosine squared, it's double when you don't do cosine squared. So notice what we've done with this integral, okay? We had 4th power. We broke that down into no power, linear, quadratic, and now we take the quadratic, and again we break it down into no power and a linear. So now everything is going to be straightforward to do. It's easy for me to say. It's not everything is multiplied by 2, what Matt said. It's just the angle is multiplied by 2, okay? So basically, however many this is doubling, okay? All right, so let's pull that quarter out. So that's going to be 1/8. The integral of 1 is x. The integral of cosine 4x is sine 4x over 4. So we've got a quarter x minus sine 2x over 4 plus that, plus c. Don't forget the plus c. Okay? How do we feel about this one? Yes? Why do I have the half here? That comes from the substitution again. I mean, the substitution is the angle squared is a half of 1 plus cosine of double the angle. Okay? So here I have cosine squared. So that becomes 1/2 1 plus cosine. And instead of square root of 2x, it becomes cosine of 4x. So this is tricky. You have to keep track of both the minus signs and what's going on with the fractions. Okay? That's what makes these hard. They're just messy. These aren't fun. All right. We'll practice another one of these. And by the way, if I made this sine to the 6th, this would be sine squared cubed. It starts to get really annoying. Okay? So I don't want it to get too bad. We wouldn't give you that. You'd have to cube it. If it was sine to the 10th, you would have you'd have sine squared to the 5th, and then there'll be this mess to the 5th, and you'd have a long chain of them. They're actually simplification formulas for doing these. So if you were doing them for real, first of all, you just put them in your computer and let Wolfram Alpha figure it out. But Wolfram Alpha uses the formula. Okay? If you're bored, you can sit down and you can just use various letters, and you'll see where the formula appears. But most of you probably have better things to do. Maybe not all of you, though. All right, so let's give you a similar one. Let's see how we do on that. So sine squared of 4x, cosine squared of 4x dx. You guys the first step, and then you can practice from there. So sine squared of 4x is going to become 1/2 1 minus cosine 8x. And cosine squared of 4x is going to become 1/2 1 plus cosine 8x dx. Okay? So that's the first step. And then I'm going to let you work on it for a couple minutes. Got it? Let's multiply this out. By the way, some of you might recognize that this is essentially the double angle formula for sine. Because sine of 2x is 2 sine x cosine x. So you could play with this and sort of skip a step but it's okay if you don't see that. So this becomes a half times a half is a quarter. 1 minus cosine squared of 8x dx. And then because you guys are all my little math geniuses here, you say 1 minus cosine squared is sine squared 8x dx. Okay, now for sine squared of 8x, I'm going to use this formula. I'm going to get 1/2 1 minus cosine of 16x. So this is going to be a quarter 1/2 1 minus cosine 16x dx. That's equal to 1/8. Okay. Integral of 1 is x, and the integral of cosine 16x is sine 16x over 16 plus a constant. You can distribute the 1/8 or not. I don't really care. How are you doing this one? Good? Not as intimidated as we were 45 minutes ago? Now let's move on to, I'm sorry? Yeah. There's other ways to do this. There's about 3 different attacks that will all work the same on this problem, but you end up in the same spot. Okay, yes? How I got this? That's 1 minus cosine squared. It's sine squared. Okay? Aren't these fun? No? Okay. No one seems to think they're fun. That's so sad. How are you ever going to be mathematicians if you don't think this is fun? I know the answer to that. All right. Let's move on from sines and cosines to secants and tangents. Wait till we do the trig substitutions, which we're doing on Wednesday. Well, we might get them in today. We might get a little in. Suppose I have something like that. I believe we did this exact problem, but we'll do it again. I see tan cubed secant cubed x. Now, if I see secant squared, so don't rewrite this. I'm just going to erase this for a second. If this was secant squared, then this would be just a straight u substitution, because I let u be tan and du would be secant squared. But I have secant cubed. So what am I going to do? Because I kind of want to have the secant squared, but if I just have a secant left over, which doesn't really help. However, the derivative of secant is secant tangent. So if I made this tan squared x secant squared x times secant x tangent x, how do I know to do this? Now you don't. Okay? If you didn't know before, now you do. Now here, the derivative of secant is secant tangent. And remember, for tangent squared, I can replace it with secant squared minus 1. So I can make this secant squared x minus 1. That replaces the tangent squared. Times secant squared x times secant x tangent x dx. So again, first I pulled out a secant and a tangent, and then I have even powers. So if I have even powers of secant and tangent, I can take the tan squareds and replace them with the secant squareds. So start to see, this depends a lot on whether you have evens and odds. Okay, so if I let u be secant, du secant x tan x dx. So this becomes the integral of u squared minus 1 times u squared du. Distribute the u squared, and you get u to the 4th minus u squared du. That's nice and simple. Okay? Remember, the whole secant x tangent x dx gets replaced with du. That's u to the 5th over 5 minus u to the 3rd over 3. So that's secant to the 5th x over 5 minus secant cubed x over 3. Does that height? That's 2. Okay? So far, so good? So how do I know to do that? Well, as I said, I don't see secant squared, I see secant cubed. And that tells me that I can take out a secant and a tangent. As I said, I gave you guys about 20 practice ones in that, exactly 20 practice ones in that document. So it'll give you a lot of chance to do these. And later, while other people are out having fun, you can sit at home and do these. Make sure you call your mother and tell her how hard you're working. Make her feel bad. All right. What if it's not the odd power? Let's try a different thing. What if this was secant to the 4th? Any ideas? Actually, wait, is that hard? Let's see. Secant squared. No. So what am I going to do? That's right. I'm going to do secant squared, secant squared. Why am I doing that? Because the derivative of tangent is secant squared, and I can take everything else in the integral and put it in terms of tangent. Slowly but surely, you should start to be seeing what we are trying to do each time. Yes? This is tan cubed x, secant squared x, secant squared x. Oh, yeah, it's supposed to be an x in there. It's all right. That's the whole, you know it's there. That's like, don't email me about that stuff. Okay? And contrary to popular belief, I don't check my email at 2 in the morning. So when you're emailing me at 2 in the morning, I'm not going to respond. If I had your phone number, I would call you at about 6:30 in the morning to punish you. But I don't. All right. So as I said, one of these secant squared could be the derivative of tangent. So I can just take the other secant squared and turn that into a tangent. Right? Because if tan squared x is secant squared x minus 1, then secant squared x is 1 plus tangent squared x. So I can now make this tan cubed x, 1 plus tangent squared x, times secant squared x dx. Why wouldn't I break up both the secant squared? I want to keep one for a derivative. Okay? Because I need to keep secant squared x dx. This is going to become du. So now if I let u be tan x, du is secant squared x dx. So this now becomes u cubed 1 plus u squared du. Why didn't I do u cubed and du squared? Because I don't know what to do with a du squared. I only have to have du. So I have to get everything in the integral in terms of something, and just the one thing left to be du. All right, distribute. And this is very straightforward from here. That's u cubed plus u to the 5th, which is u to the 4th over 4 plus u to the 6th over 6. And that's tan to the 4th x over 4 plus tan to the 6th x over 6 plus a constant. So again, the controlling thing here is the power of secant. It's secant squared or secant cubed. If it's just secant, we memorized what the integral of secant x is, remember? We wrote those down. I'll put them on the board again. The integral of tangent x and the integral of secant x. The integral of tangent x is negative ln cosine x plus a constant, and the integral of secant x is ln of secant x plus tan x plus a constant, whatever. I'm not going to put the constant. Okay? You should already have those written down from the other day, yes? And you should memorize the integral of natural log of x. Yeah, I'll put up a page of integrals you should know. Spring vacation, while the rest of you are off getting tan and having fun and not having alcohol because you're under 21, I will be sitting in my office alone, cold, in the dark, thinking of things to make your math lives better. Eating cold beans from the can with no one there to look. But I'll be okay. Anyway, so yes, I'll make you a page. I already have it somewhere, I just have to find it. All right, let's do something slightly different, but related. These really hurt your brains, so brace yourselves. I'm just going to erase everything. If you didn't get it down, then watch the video. Copy it from your friend. Okay. What if I wanted to do the integral of the square root of 1 plus 9x squared dx? You look at this, and you reach into your bag of tricks, and you say, u substitution. I could let u equal 1 plus 9x squared. The problem is du is 18x. I don't have another x term. What about that whole u, and then the u equals something, and then it's subtract? No, that's not going to work either. There's no trigonometry in there. Integration by parts. Well, if I let this be u, that's really messy. And that would be dv, that just comes out x. What do I do? Here's what you do. You make a substitution that does the following. Let tan theta equal 3x. How would I ever know to do that? Now you do. Okay? There's families of these. I know. This kept mathematicians busy for a couple hundred years. Okay? Each time somebody else would come along and go, I got a new one for you. Then they'd rack their brains for a while, and then somebody clever would figure it out and go, and then they'd all say it's easy after that. So if I let this be tan theta, now why? You'll see in a second. Okay? Then secant squared theta d theta is 3 dx, or 1/3 secant squared theta d theta is dx. Okay, I picked a hard one to start. My apologies. Now, why would I do that substitution? Well, now, if 3x is tan theta, then tan squared theta is 9x squared. And that would become the square root of 1 plus tangent squared. And then for dx, I put 1/3 secant squared theta d theta. And we'll spend more time on these on Wednesday. What is 1 plus tangent squared? It's secant squared. So this is now the square root of secant squared. The 1/3 goes out here. Secant squared theta d theta. Brace yourselves, it's going to take the whole board. What's the square root of secant squared? Secant times secant squared. So this is now going to become 1/3 the integral of secant cubed theta d theta. Whew. All right, now we have to integrate secant cubed. We did this at the end of the last class, but we'll do it again, because a lot of people at that point, their little heads had burst, and they said, I'm done. They wrote it down, but they weren't really paying attention. So the integral of secant squared is the following. I'm not going to worry about the third for the moment. The integral of secant cubed, break that into secant theta, secant squared theta, d theta. Now we do integration by parts. Why can't I do u substitution? Or why can't I do a substitution? Well, if I made this 1 plus tan squared, the problem is the derivative of tan is secant squared. So why don't I do this? Let u equal secant dv secant squared theta d theta, and du is secant theta tan theta d theta. V is tan theta. Okay? So let u be secant, derivative of secant is secant tangent. dv is secant squared, antiderivative of secant squared is tangent. So now I have integral of secant cubed theta d theta is u times v, which is secant theta tan theta, minus the integral of secant theta tan squared theta d theta. And what's tan squared? Secant squared theta minus 1. So I get the integral of secant cubed theta d theta, secant theta tan theta, minus integral of secant theta times secant squared theta minus 1. I have run out of space, so I'm going to have to squeeze this a bit. Well, I can squeeze in one more row. This, now distribute. You get secant theta tan theta minus the integral of secant cubed theta plus the integral of secant theta d theta. And notice I've got the minus secant cubed here and the secant cubed there, so I can add it to the other side and I'll get 2. The integral of secant cubed theta d theta equals secant theta tan theta plus the integral of secant theta, which is log of secant theta plus tan theta plus constant. And the whole thing's multiplied by a third. So this becomes 1/3. Got to divide that by 2. 1/2. I'm not even close to done. Secant theta, tan theta. I am actually close to done. I know, I'm just torturing you guys. Plus log secant theta plus tan theta plus c. So, whew. But wait. Okay, so that's the integral. I mean, it's big because I wrote all over the board. So let's start over to make sure everybody understands. Okay? We had 1 plus tan squared times 1/3 secant squared. 1 plus tan squared is secant squared. Squared of secant squared is secant, so this became secant cubed. Sorry, I picked a hard one to start with. the integral of secant cubed is going to be secant times secant squared. Do integration by parts. Let u equals secant, dv equals secant squared, du equals secant tan, v equals tan. So you can rewrite secant cubed as secant tan minus secant tan squared. Then you let tan squared be secant squared minus 1, distribute, add the secant cubed to the other side, and now you're just left with this one integral. So we're all the way down to here. We've done the integration. And then there's just one fun thing you have to remember. This isn't in terms of theta. This integral is in terms of x. So what do we do? Because we've done the whole thing, but we did the whole thing in terms of theta. So if tan of theta is 3x, okay, then that means, draw a little triangle. The tangent of theta, you could say this is 3x, and that's 1. So Katoa, that's the square root of 1 plus 9x squared, which, by the way, is this. So wherever you have secant theta, you can substitute square root of 1 plus 9x squared. For tan theta, you can put in 3x, square root of 1 plus. So remember what I told you about how derivatives and integrals are much harder. You think this is bad. I didn't have a teacher to help me with this. They just sort of assigned it and said, good luck. You get 1/6 secant theta, which is square root of 1 plus 9x squared, adjacent over opposite, hypotenuse over adjacent, times tan theta, which is 3x, plus the log of the absolute value of secant theta, plus 3x, plus a constant. And as I said, you would never look at that and say, oh, well, it's just this, okay? So this is why integration is so much more difficult than differentiation, okay? Because the derivative of this isn't hard at all, but the integral is ridiculous. Now, I accidentally picked a really hard version, so now I'm going to give you an easier one that we're going to do. Okay? I know. Look at the bright side. A week from now, you'll be in Florida, Paradise Island, Massapequa, one of the garden spots of Long Island. Maybe if you're really lucky, you'll be in Wyandanch. It's okay. I've been to Wyandanch. I've been there twice to Wyandanch. It's okay. All right, we ready? I'm sorry, Matt? Where did I plug back in? Well, once I know that I took tan theta and I said that was 3x, right? That this means that I have a triangle where the tangent of that triangle is 3x over 1. So I can find the secant and the sine and the cosine and all of that. Let's do another one. I'm going to erase. Good. Yeah. Aren't you glad you came today? Your friends who didn't bother to come to class today, you can make fun of them and say, no, I will not give you the notes. You earned the notes today. All right, square root of 1 minus 4x squared. I'm going to let sine of theta equal 2x. Wednesday, I'll show you why I picked these substitutions. Because this can now be 1 minus sine squared. Okay, then cosine theta d theta is 2 dx, or 1/2 cosine theta d theta equals dx. So let's substitute. If sine of theta is 2x, then sine squared of theta is 4x squared. So this becomes square root of 1 minus sine squared. And dx is 1/2 cosine theta d theta. So far, so good? Don't worry, we'll show you the substitutions. Okay, as I said, there's pattern to this. So all I did was I took 2x and I made it sine theta. Notice that's the square root of 4x squared, okay? So square root of that I made sine theta. So when I square it, you get that, okay? So what's 1 minus sine squared? The same as cosine squared, and the square root of cosine squared is cosine times cosine. Is cosine squared theta d theta. And we know how to do cosine squared because we did a bunch of those. So you do the substitution. This is going to be 1/2 integral of 1/2 1 plus cosine 2 theta d theta. See why we learned the trig ones first? Yes? Yep. Nope. What's the square root? Remember, this is the square root of cosine squared. Okay? So 1 minus sine squared is cosine squared. The square root of cosine squared is cosine times cosine. Okay? Again, somebody thought this, and everybody else was like, wow, I hadn't thought of that. So this is a relatively easy integral for us. The 1/2 times 1/2 gives us a 1/4. You get theta plus sine 2 theta over 2 plus a constant. And now for the fun part. Remember, this is in terms of theta. So you have to go back and figure out sine and cosine. You say, okay, so I have a triangle. The sine of theta is 2x over 1. So the missing side, the adjacent side, is the square root of 1 minus 4x squared. It will come out to be this, if you do it correctly. So we get 1/4. So what's theta? Theta is inverse sine of 2x, or arc sine of 2x. You wouldn't have seen that coming. And sine of 2 theta, sine 2 theta. Sine 2 theta. What do I do with sine 2 theta? Well, here's another one you probably forgot. Let's put this over on our board here. We'll squeeze it in. Sine of 2x is 2 sine x cosine x. You guys are supposed to remember this. Remember when you memorized them and you forgot them, and then you memorized them and you forgot them, and you memorized them and you forgot them? One more memorization and you're probably good. I know, but the Regents gave us a formula sheet, so why do we have to memorize it? I know, it's not fair. I understand. I have a head start on you guys. So sine of 2 theta is 2 sine theta cosine theta. So this is 2 sine theta cosine theta over 2. So it's a 1/4 arc sine 2x. Sine of theta is 2x. Cosine theta is the square root of 1 minus 4x squared plus c. So how do you know which substitution to do? Well, there's basically 3 sets. We only did 2 of them today. If you have a squared minus x squared, right, you're going to let x equal right. You're going to let x over a equal sine theta. And I'm going to do these again on Wednesday, so you don't really need to write them down. If you have a squared plus x squared, you're going to let x over a be tan of theta. And if you have x squared minus a squared, x over a will be equal to secant of theta. I have to double check these, okay? But I'm 98% sure it's correct, but not 100. Okay? Then these work out very nicely. So we'll practice some more of these on Wednesday. Like I said, the practice problems will be available at 5